Okay, we're going to keep talking today about statistical learning, and I'm coming back to the website that we saw last time for the book, and I'm going to get some more slides for us to look at. Last time we looked at the intro slides. Today we will look at statistical learning slides, Chapter 2. All right. So remember that the statistical learning idea is mostly to do with predictive modeling. So trying to make a prediction for a numerical variable on the basis of input variables or for a categorical variable. The authors of this book call the former case, where you have a numerical variable that you're trying to predict, regression. And the latter case, where you have a categorical variable, they call that classification. Classification as in you're trying to assign individuals to predefined classes, like cancer or not, or tumor class A, B, or C. Right. Okay. We are going to think in terms of a model, a statistical or probabilistic model for some response variable, y, which could be numerical or categorical, in terms of some input variables. So we're going to use x, or the authors are going to use x as the indication of input variables, predictor variables. So for example, if we wanted to predict sales in terms of three input variables, predictor variables, TV, radio, what is X3? I don't know what X3 is. They didn't tell us. If we wanted to predict sales in terms of characteristics of an advertisement, say, was it on the TV or was it on radio or whatever? We allow for a systematic relationship between the response and the predictors. So y equals some function f of the input variables plus some random error. So the random error, those epsilons, are there to allow for the fact that we're not going to actually see a deterministic relationship in practice. We have data randomly obtained from a population, so there's random variation. We think that underneath, like underlying our data, is a systematic or deterministic relationship. But what we actually observe is that relationship with some random error piled on top. So if you're familiar with linear regression, this is one way to write a linear regression model. You could say blood pressure equals f of some input variables. So this could be intercept plus, like beta 0 plus beta 1 times gender plus beta 2 times age plus ... That would be a linear model because you're saying response can be written in terms of a linear combination of your covariates. You don't have to use a linear model, but linear models are widely used because of their simplicity and interpretability. Okay, so if we can estimate F, whatever it is, then we can make predictions. So if I want to make predictions, what I want is a hat on top of F, an estimate of F. Then what I would do to make a prediction for an individual with a certain collection of input variables is plug in those input variables to the estimated F. And whatever that equals, call it a Y with a hat on top of it. An estimated value of Y would be my prediction. Keep moving here. Okay, if we had a numerical response variable, call it Y, blood pressure or stock price or whatever, and suppose we just had one input variable X, we could draw a scatter plot of X versus Y. So here is that scatter plot. Gray dots are individuals in our data set for which we have, each of whom we have X and Y measured. F of X, Y equals F of X plus random error. That red curve is an estimate of a systematic relationship between Y and X. The red curve is F hat, the estimated F. It's not a linear model in this case. So however they fit this model was not a linear model because that's not a line, it's a curve. Okay. The value of the line, or the curve, at a particular value of X. So you tell me the input values, what is your prediction? Or what is my prediction? It's the function, it's F, evaluated at those input variables. In this case, there's only one input variable, so my prediction is just F hat, red curve, evaluated at X equal to 4. That's my prediction. So for the next individual that comes in with X equal to 4, for whom I don't know Y, my best guess, according to this model, is that red dot. That red dot is, in probabilistic terms, the expected value of Y when, or conditional on, X equaling 4. It's an expected value, which is just a fancy average. Okay, we could have fit this curve in a variety of ways. This looks like a pretty good, that red curve looks like a pretty good fit to this picture. What if we had used a linear model instead? So we could have, with those same data, just kind of roughly picture them again. If those were our data, and we, from the book, had this estimated function F, we could have used a different model. Who's to say that's the best model? It looks okay based on my eyes, but suppose we did a linear model instead. We might have fit a linear model. That's not a perfect line, but it's supposed to be a perfect line. That doesn't fit quite as well, doesn't look like. Yet another possibility for fitting the relationship would be to fit it perfectly, so interpolate. That fits it perfectly. Surely that's the best choice if it fits the data perfectly. But we've, I think, talked about this potential for overfitting the relationships that our data suggest. The goal with statistical learning is to learn a systematic relationship and then apply it to new data from the population. I don't want to just perfectly perform on my training data because my training data were randomly obtained. So the next individual that I'm going to observe is not from my training data. So I don't want to overfit my training data. it is possible to overfit your training data. The blue linear model is the least likely to overfit out of these because it's the least flexible. The green curve is the most likely to overfit, and the red curve is somewhere in between. So which one would you want? How do you kind of formalize distinctions between these? Each of these are valid models. These are all possible models that you could use for this data set. Which one would you want? With a numerical variable, a natural way to quantify how well you do in capturing the systematic relationship is the mean squared error, mean squared prediction error in particular. So the mean squared error is something that you use in linear regression. That's the fitted values minus the observed values, square that, and compute the average of those. So for every individual in your data set, we could come for the red curve, say, and we could ask, what's the difference between observed and predicted? What's the difference between observed and predicted for all of these? All these little deviations, these errors. If you squared each one of those errors, some of them are positive, some of them are negative. If you square each of them, then they all become measures of difference. So if you then averaged that up, that's a natural measure for how different overall your curve is from the data. So mean squared error is what we were talking about in this slide here. The expected value, the mean of observed minus, they're saying g of x, we'll call it f hat of x squared. So the expected squared difference between truth and prediction. So the ideal predictive model would be the one that minimizes this. We need to put an asterisk next to that statement because the function that minimizes the mean squared error on the training data is which of these three? Which one? Be the green one, because the green one is perfect. On the training data, it's perfect. The mean squared error for the green one on the training data would be 0, actually, because there's no errors. Fitted equals truth every time. But we know that there's something wrong with that. Just because that has perfect mean squared error on the training data, that may not be the one we want. So we're going to keep talking. Some of this is more relevant than others to us. One possible simple model is a linear model. We said this before. We could say that f of x, linear model f of x, is a regression model. Intercept plus x1 effect plus x2 effect plus ... That's one possibility. And we could fit this model in the usual way, doing regression. So LM, for example, in R. While a linear model is almost never strictly true, real life is almost never perfectly linear, even so, this often does well at capturing the essence. It also tends to do well at fitting the training data well without overfitting the training data. So linear models are a good starting place. This is all one input variable that we've been talking about so far. We've just made scatter plots of y versus x. But of course, in practice, we would be interested in more than one input variable. So here's a picture for two input variables. Y is income, vertical axis. And now we have two input variables, years of education and seniority. But the problem is still the same thing. There's some systematic relationship between the input variables and the response. And we want to fit that relationship. F of vector x, F of years of education and seniority. So when we move into more than one input variable, we get into multiple dimensions, and it can start looking complex, like this surface. This is not a line. It's not a linear surface. It's not a plane. It's some curvy surface. So the same idea applies, just a little more complicated. I want to estimate a surface. You could do that in a more or less flexible way, just like when we were looking at the scatter plot. Here's the 2D analog of a linear model. It is beta 0 intercept plus education effect plus seniority effect. And that's a plane. So there's no curviness to this. Here's a more flexible version of that. And an even more flexible version that perfectly interpolates. So that sequence of slides is analogous to these three pictures right here, starting from very simple, not very flexible, but not very likely either to overfit, to something probably better because it has some flexibility, but it did not interpolate, to probably overfit because we interpolated the data. How do we know if we overfit? We're getting there. So we're going to see some ways that we can get trustworthy estimates of accuracy, basically. Linear models are easy to interpret because, for example, you could go to the beta coefficient for gender, and you could interpret that as the gender effect. This is the way that gender contributes to my response. If, on the other hand, I have a fancier model, like this one is not written in a linear way. This is not written as beta 0 plus beta 1 education plus beta 2 seniority. So one simple way to kind of illustrate this is, suppose we put education and education squared in the model, seniority and seniority squared in the model. That would make this be curvy. It would allow this to be curvy, more flexible. But as soon as we put those squared terms in, it's harder to interpret things. What's the seniority effect now? It's not beta 2. It involves two coefficients now because seniority and seniority squared are in there. So the point here is that there are differing levels of interpretability. We need to be able to address this issue of overfitting. We don't want to overfit, but we do want to fit well. So how do you balance it? The linear model is relatively simple. And even if we were to look at linear models, like in the GWAS case, where we have thousands of SNPs maybe, we might want to say logistic regression for case control status in terms of all of my SNPs, thousands of SNPs. Maybe I have too many variables to get an accurate model using them. So maybe I can pick a subset of them, fewer variables, and you can actually increase your performance by throwing out some variables. And in addition, you have this benefit of a simpler problem to interpret. If I have 100 SNPs instead of 1 million, much better chance that I'm going to be able to like interpret things from the model output. This is a nice picture on the trade-off between the interpretability of your predictive model, like the gender effect in terms of predicting whatever is such and such. The ability to make statements like that on the vertical axis versus the flexibility of the model on the horizontal axis. Flexibility speaks to, does it have enough wiggle room to accommodate curviness, for example. So, for example, least squares think of that as just linear regression, like a numerical response, and we have some predictor variables. We're going to say the mean of y is beta 0 plus beta 1 input variable 1 plus beta 2 input variable 2, ... So this is not terribly flexible because it's restricted to being linear. No curviness allowed. It is relatively high on the interpretability scale, though, because a linear model is pretty easy to interpret. Even better in terms of interpretability is if you were to do some feature selection. Suppose we have 1 million SNPs. If we did some looking, chances are we could whittle that down to a smaller number. Subset selection and the related, more sophisticated technique of lasso are variable selection techniques. We'll see both of them soon. So these are like regularized or restricted versions of regression. Over at the far right, we have the more complicated, the more complex, more black box-like algorithms for doing prediction, like trees that have some sophisticated postscript stuff on them called bagging and boosting. Support vector machines, neural networks would be down here as well. Very flexible because these are nowhere near restricted to being linear. They can be very flexible, but also very low interpretability because of how complex they are. Think of these like black boxes. You just pour in the input variables and they spit out a prediction. But you don't have a model in front of you that you can easily look at and say, oh, the gender effect is such and such, the contributions, relative contributions of these variables is so and so. Okay. So often, depending on what your goal is, that may have impact on which of these methods you look at. If you want like a quick, dirty, simple, interpretable classifier, you probably will be happy with regression, logistic regression, and some of the simpler techniques. If you work for an enormous company and they have tons of data and all they want is an extra 0.5 percentage point profit each month, I don't care about the insight so much, I just want the most accurate prediction as possible, then a black box sophisticated algorithm is maybe going to be your friend. Black box sophisticated algorithms will tend to outperform the simpler ones, although not in every case. And in particular in omics applications, where we have thousands and thousands of features, genes, SNPs, proteins, but many fewer actual observations. Our matrix in omics applications tends to be many more rows than columns, more features than individuals. In the statistical literature, that's referred to as N much less than P. High dimension, your dimensionality outpaces your sample size. Classical multivariate statistics is expecting more observations than variables. So principal components and discriminant analysis, cluster analysis, all that stuff was originally developed under the expectation that that would hold. Omics, we have that most of the time. So where I was going with that was, while these have a lot in their favor for their ability to capture complex relationships, these are not so flexible, but there's some interesting theory that says even when this is nowhere near to flexible enough to capturing the truth, you may do better using a simple method like this than a more sophisticated one like that in these cases. When there's not enough observations to really fill in the blanks of a complicated nonlinear model, you may do better by just treating it like it is linear. I'll show you some examples of that. By better, I mean you may actually have a higher accuracy in the general population using a simple method than a really sophisticated one. Okay, so now we get to the question that I alluded to earlier. How do we balance, flexibility with interpretability and accuracy in particular? With a numerical variable, mean squared error is the natural quantity to look at. How accurate is my model? Let's look at mean squared error. But we already said we have to be careful about how we compute that. And in particular, this slide is going to draw a distinction between two different mean squared errors. There is, first of all, the mean squared error that you would get if you applied your model, the one you fitted to your training data, if you applied that back to the training data. So you have some individuals with cancer and some individuals without cancer, and you have thousands of features. You fit a model, let's say a logistic regression model. Well, we're doing MSE, so let's do a numerical response. Let's say we're trying to predict prostate-specific antigen, so some protein level. We have PSA measurements for some people with prostate cancer and PSA measurements for some people without prostate cancer. And for each of those people, we have omics data. So we have thousands of gene expression measures, maybe. Those are our training data. They're training because we know the answer, we know the value of the variable of interest. The variable of interest in that case would be PSA. I want to predict PSA given your genomic profile. So suppose we have 50 people with 50 people. Let's say we have 100 people, and for each person we have PSA measurements and omics data. We could fit a model, like say a linear model, with those 100 people. And then for each of those people in my data set, we could plug in their input variables to our fitted model to get an F hat, a predicted value of Y. If you were to compute the average squared difference between observed and predicted values on the training data, you'd get a mean squared error on the training data. Okay, that's nothing new. That's what we talked about doing in those scatter plots that we were looking at. And these may be biased. The reason they may be biased is, oops, why am I doing that? Go back here. I'm going to let them say it. They could be biased. I'll show you why in a second. What we really care about in terms of telling how confident we are in our predictive model is how accurate will it be when we take it out to the general population. We're trying to predict PSA. We have 100 people for whom we know PSA. The intended use of the model, though, is, say, in a clinic where a new person walks in the door and they give us an omics data set, so we maybe genotype them on some SNPs or something, plug that data into our model and get a Y hat for that person. We don't know their PSA level. I'm going to predict it. I want to know the mean squared error in the general population. So not on the training data, but on a held out, fresh, new sample of data from the population that we'll call a test data set. the ideal way to assess how accurate your model is, your predictive model is to build it and use MSE as your guiding measure to pick a good one, but ultimately to assign a confidence measure to it, use the accuracy that you get on a new set of data, not the data that you used to build the model in the first place. By doing that, by holding out some new data that came from the same population, by holding them out and not using them when fitting the model, it's not possible to overfit these data. They weren't used. So now when we apply the model to them, this potential issue of overfitting is going to be exposed. Because say we picked the green curve. We fit the crap out of the training data perfectly, but when we apply this to a new set of data, so here comes a new sample from the same population, and it's just a little different because it's a new random sample. So if we picked up the green curve and sat it on that sample, it's not going to interpolate anymore. Does that make sense? This scatter plot, we'll call it our training data. Those are the data for which we know the answer to the variable of interest. And we're going to use them to model the relationship between variable of interest and the input variables. Down here are testing data, or test data. These were not used. These were not in that picture at the top. The green jagged curve fits the training data perfectly. If you picked that curve up, if we redrew it, I'm not going to be able to do it very well, but if I tried to redraw this, that doesn't interpolate the test data. It's a new data set. So that's going to bear out when we ask for accuracy on the test data. I'm going to get, whereas I had an MSE of 0 on the training data, it's not going to be 0 anymore with the test data. So even though the green curve seems to be clearly better than the red one, for example, in the top picture, it may well not be down here. In terms of mean squared error, chances are the smooth curve is going to win. Okay, so this is a good picture. Here is a simulated scenario. We have a numerical response and one predictor variable. The true deterministic relationship, or the true systematic relationship between y and x, is the black curve, left panel. What we see, the actual dots, are plug in x to that curve and then add some random variability, some plus or minus. So the scatter plot is following the black curve. And then what might we do to fit a predictive model? There are two, let's see, there's three. Red curve, gray curve, orange, blue, and green. Different flexibilities. Okay, there are three fitted models represented in the left panel. There's an orange curve, a blue curve, and a green curve. And those are going from least flexible to most flexible. The orange curve is a line, looks like to me. Just a line going through the points. Does the best it can within the restriction of being a line. The blue curve is a smooth, pretty smooth curve. Not linear, but not nearly as wiggly as the green one. So the green one is the one that's kind of trying to interpolate. It's a little too, or it's very flexible. Okay, three different choices. And then let's look at the right panel. So this is the mean squared error. The curves were drawn, like the red curve and the gray curve were drawn across a spectrum of complexities, but the yellow or the orange blocks correspond to the linear model. The blue blocks are the blue curve, and the green blocks are the green curve. So what are these two different curves? The gray curve, let's look at that one first. The gray curve is the training error, mean squared error on the training data. And as you go from less to more flexible, you get better. Get better and better and better at modeling the training data, to the extreme that if you interpolated, you'd have 0 mean squared error on the training data. The red one is the test error. So let's take a new held out sample of data from the same population, run it through our model and make predictions, and now let's look at mean squared error. And this is where the insight is. Simple, not quite so simple, gained us quite a bit. So I improved quite a bit by going from linear to the blue curve, the middle of the three. But when I made it even more flexible by going to the green curve, it actually hurt. The mean squared error on the test data went up when I allowed for this amount of wiggliness. That's a picture of overfitting. So the curve going up over here, that's overfitting. We have overfit the training data. So when you're doing analytics or statistical learning, predictive modeling, you will probably end up with a picture like this one, where you try to say, where's the sweet spot of model complexity and accuracy? And it's not guaranteed to be the simplest. It's not guaranteed to be the most flexible. Probably going to be somewhere in the middle. Here's another example that's also informative. We have, again, the same setup. Black curve is the true relationship. In this case, the true relationship differs from the previous slide in that it's much less curvy. So the black curve is almost linear. It's not quite, but it's pretty close. And here again, we have the three models that were considered in the previous slide. We have a linear one, which is orange. We have a slightly curvy one, which is the blue one. That's kind of hard to see. The blue one is a curve, but it doesn't have to be noticeably curvy. Like if you were to say fit a quadratic to this relationship here, it would look pretty linear because the relationship itself is pretty linear. So the blue curve does pretty well as also in this case. The green curve tries again too hard to follow the nuances of the training data. So here's the picture like from the previous slide. In this case, because the truth is nearly linear, the linear model does nearly as well as the more flexible one, the blue one. Training or test error, the more generalizable error rate, is nearly the same between the linear and the sort of smooth one. Whereas the green one, again, shows us evidence of overfitting. Here's another scenario. The point is that it depends on the nature of the relationship, and you really need, in order to pick among models, what you really want is an estimate of the test error. Not the training error, the test error. This is important. There is the mean squared error, the expected value of observed minus fitted quantity squared. you can write that algebraically this way. It is equal to the variance of your model, of your fitted model, plus the bias of your fitted model squared, plus just the random variability of the data itself, that residual variability about F or around F. This variance of epsilon, the residual variability, you can't do anything about it. This is what it is. The variance in the population is what it is. But you can pick F however you want. And in terms of minimizing the mean squared error, you want, therefore, to minimize two things, both the bias of the model and its variance. So bias speaks to, like in this picture, the line is biased. It does not follow the right pattern. So for example, in this region right here, when you predict y for given values of x, they're going to be biased because they're restricted to be on this line, which is systematically below where everybody else is. So that's bias. That's a problem. But the other piece that goes into mean squared error is the variance of the model. What does that mean? That means if we were to go get a new sample of, say, 100 individuals from the population that these were drawn from and make a scatter plot and fit these curves again, which of these three curves do you think is going to differ most on a new sample that comes in the door? It's going to be the really wiggly one. The really wiggly one, when you give it some new data, it's going to change quite a bit because it's got to wiggle to accommodate the new data. Whereas the line is not going to change very much. Chances are the new data are going to qualitatively follow the same linear pattern. So a linear model is not highly variable, whereas this interpolating model is highly variable. In terms of getting the sweet spot, minimizing a mean squared error, I need to find a balance between bias and variability. The more biased a method is, the less variable it is. And conversely, the less biased it is, the more variable it is. Okay. This is the same picture from the three examples we just went through with these quantities added in. So we have bias and variance and mean squared error. So as you increase flexibility of your model, the variance increases and the bias decreases. And here's what happens to the mean squared error in this particular scenario. This was this simulated scenario. In that scenario, this is the relationship. That's the trade-off between flexibility and mean squared error. So the optimal model is right there. It's the one that achieves the lowest mean squared error. See how much more we have here. Almost done. I think I can get through this. So all of that was regression problems where we have a numerical response like PSA levels or income or stock price or whatever. We might instead have a qualitative or categorical response variable, in which case it's called classification. But it's the same idea. You want to predict y based on input values for x's. Okay, with a categorical response, we don't talk about mean squared error anymore. Mean squared error is not the natural way to characterize performance with categorical. Instead, what we focus on with categorical response is the error rate, the misclassification rate. So you are either cancer or normal for each person. When I make a prediction, I'm either correct or incorrect. So of all the predictions I made on my test data, say, suppose we have a held out set of data for which we know the answer, but they were not used in building the model. If I make predictions for them, then the number I'm going to use to quantify my confidence in the model is the proportion of those test observations that I got wrong. The misclassification error rate. What proportion of the test individuals did we incorrectly classify? Mean squared error for numerical response, misclassification rate for categorical response. The same issues apply in terms of trade-offs between flexibility and interpretability, between variability and bias. So we still have this issue of a linear model may do very well even when the relationship is not linear in some cases. This is one classification algorithm illustrated. It's called the k-nearest neighbors, or KNN algorithm for classifying. It's a very simple algorithm. What it does is, like in this case, we have two input variables, x1 and x2. So this is minus the little grid of little dots. The open circles are data points. So those are individuals in our training data. Here's an individual for which we had x1 value equal to such and such, and x2 value equal to so and so. For each of these individuals, we know class membership. So suppose this is cancer versus normal. What we would end up doing to build a classifier is, in k-nearest neighbors, we would come to each individual and we would find the k, you tell me what value of k you want to try, we would find the k individuals that are nearest in a vector sense. Who's closest? Who are your k nearest neighbors? You find the k nearest neighbors and then you ask, what are the class memberships of those k nearest neighbors? And I'm going to assign this individual to be in the class that is the majority of the rest of them, of the neighbors. So go find the k nearest neighbors, and suppose 60% of them are purple, 40% of them are yellow. I'm going to classify the current individual that we're assessing as purple, because the majority of his or her neighbors are purple. Simple idea, k nearest neighbors. K-nearest neighbors can be very flexible as a model. There's no linearity going on here. There's no linear assumptions or anything. It's just these neighbors, which can be highly irregular. So here's a picture. The dashed purple curve is the truth. That is the true region that distinguishes the two classes. If we did a highly flexible version of the k-nearest neighbors algorithm, we might see something like the black pattern. Pretty irregular, very jittery. As opposed to k equal to 1 and k equal to 100. So choosing k is not trivial. We're going to show you, we're going to see, we're done, we're out of time, but we're going to see for an algorithm like k-nearest neighbors, where we have to pick something that there's no perfect answer for, k. Should it be k equal to 1 or k equal to 100? We're going to use some techniques for tuning the model to pick k. How would you pick k in practice? Same way we've been talking about picking between models in these slides. What I would like to do is find the version of, if I'm married to K and N, let's find the K and N model, the value of K, that strikes the best balance between bias and variance. So I could do that, for example, if I had test data. Test data, not these individuals, but new individuals that were not used in making this picture. Let's make predictions on them and take a misclassification rate for K equal to 1, for K equal to 5, for K equal to 10. Do it for a bunch of Ks and pick the value of K that did best on the test data. Not the training data, the test data. That's what they did in this picture right here, actually. So K is on the horizontal axis. It's actually 1 over K. So as K increases, you actually go to the left. And orange is what you really care about, the test errors. Bluish is the training errors, which can mislead you. So decreasing K makes you better on the training data. But beyond a certain point, it makes you worse on the test data. So if these were my data, I'd come right here and I'd say, let's do K nearest neighbors with K equal to 1 divided by 0.075, say. All right, we are out of time. Next time we'll keep talking about this stuff. I'll show you some examples with omics data. You can do K nearest neighbors classification with, say, the con data that we saw last time. But we're going to learn several more techniques for classification. Most of the time when I'm doing statistical learning, it's classification. I've had projects where we've done both, but in omics cases, from my experience, most of the time it's classification. If you're doing GWAS and you have a numerical response, that's not classification, but a lot of it is classification. All right. We'll stop there, and I'll see you Wednesday.